Financial sentiment analysis is everywhere, but it's fundamentally blunt. Telling a trading algorithm that a StockTwits post is negative doesn't tell it what triggered that negativity, who's expressing it, or how strongly it's tied to a specific asset feature. In financial NLP, flat polarity labels have hit a ceiling. The real alpha isn't in knowing the direction of sentiment, it's in capturing the granular semantics of opinion. This research tackles that exact gap. We're taking the StockEmotions dataset, which already contains human annotated labels across 12 investor emotion categories, and enriching it with structured opinion graphs derived from the unified opinion concepts ontology. We then feed those semantically grounded graphs into a hybrid transformer graph neural network architecture to see if fine-grained opinion semantics actually improve emotion classification. The results show that structured semantic enrichment isn't just theoretically elegant. It delivers statistically significant performance gains, particularly for nuanced and negative emotional states. Let's start with how we actually generate these opinion graphs at scale. Manually annotating financial microblogs with granular opinion structure is prohibitively expensive, so we use a declarative LLM pipeline built on DSPy. Instead of writing brittle, hand-tuned prompts that are highly sensitive to model versioning and temperature, we use the Multi-Prompt Instruction Proposal Optimizer, or MIPRO. MIPRO automatically generates prompt proposals, evaluates them against in-context examples using a Bayesian-inspired lookup, and selects the instruction demonstration pairs that maximize annotation quality. This programmatic approach eliminates prompt model confounding variables and ensures reproducible high-fidelity outputs. The LLM maps each sentence to a strict UOC schema. Every opinion is decomposed into 5 core components: the holder, which is the span expressing the opinion; the target, the coarse-grained entity being discussed; the aspect, which captures the specific attribute or property of that target; the qualifier, which contextualizes the opinion to a subgroup or condition; and the sentiment, which breaks down into polarity, intensity, and the exact textual expression. For example, a sentence about battery life gets parsed into explicit spans, relational edges, and sentiment attributes that form a directed subgraph. This transforms unstructured text into a machine-readable semantic structure. Now, how do we actually use these graphs inside a classifier? Standard transformer encoders like BERT and BERT process text sequentially and pool representations at the sequence level. They miss the relational structure embedded in opinion graphs. To fix this, we inject the semantics using graph attention networks, specifically GATI-v2. Here's the pipeline. First, we extract opinion subgraphs per sentence. Node features are initialized from the transformer's hidden states. For each text span in the graph, we apply mean pooling to extract a fixed-dimensional node representation. Edges encode the relational flow between holder, target, aspect, qualifier, and sentiment nodes, with edge attributes explicitly carrying the sentiment polarity. We then run multi-head GATI-v2 message passing. The attention mechanism computes coefficients that aggregate neighborhood information, but crucially, it incorporates those edge attributes into the attention weights. This means the model learns to weigh semantic relationships based on sentiment direction, not just textual proximity. After message passing, we sumpool the node features to get a graph-level representation, map those graphs back to their parent sentences, and compute a mean projection per sentence. We then fuse these graph-derived features with the original transformer sequence embeddings. We experiment with 3 distinct fusion strategies. The first is simple concatenation, where we stack the text and graph vectors and project them back to the original dimensionality. The second is a learned gating mechanism. We compute a sigmoid gate over the concatenated features and use it to dynamically weight the contribution of raw text versus opinion semantics. The third is dot product attention, where we treat the graph features as queries and the text features as keys and values, allowing the model to attend to semantically relevant spans. Across all fusion types, we add a residual connection scaled by a hyperparameter to preserve the original textual context and prevent semantic drift. We run Bayesian hyperparameter sweeps over batch sizes, GAT output dimensions, attention heads, fusion types, and residual scaling factors to find the optimal configuration. The results tell a clear story. On the StockEmotions dataset, fine-tuned encoder models consistently outperform zero-shot large language models on this specific financial emotion classification task. The most significant gain comes from the BERT-GNN variant. Adding graph semantics pushes the macro F1 score from 33.25 to 37.88, a gain of over 4 points that passes strict statistical significance testing. The improvement is driven by stronger performance on anxiety, excitement, and ambiguous emotional states. BERT-GNN shows a more modest absolute increase, but McNemar and Stewart-Maxwell tests confirm a statistically significant redistribution of predictions, particularly improving classification of depression and disgust. What's especially interesting is how the models handle emotional granularity. Confusion and optimism are consistently the easiest categories to classify, peaking above 60% F1 for the top encoders. Ambiguity and belief remain challenging across the board, with F1 scores hovering in the low 20s to 30s. Zero-shot LLMs like GPT-5 and QN3, 5-35b struggle disproportionately with negative and ambiguous emotions, often dropping into single-digit F1 scores for disgust and belief. This suggests that while large generative models are powerful few-shot reasoners, They lack the task-specific semantic grounding that structured opinion graphs provide. When you need reliable detection of nuanced financial sentiment, fine-tuned encoders with explicit graph-based semantic injection still hold the edge. Mapping predictions to broader taxonomies like Ekman's basic emotions and Go emotions, valence groups reinforces these findings. The BERT-GNN architecture achieves the highest valence macro, F1, primarily driven by gains in positive and ambiguous classifications. BERT-GNN shows a redistribution effect, trading some positive classification precision for improved negative and ambiguous detection. The generative models maintain strong positive detection, but falter on negative and ambiguous valence, which drags down their overall macro performance. This work demonstrates a practical blueprint for moving financial NLP beyond flat sentiment labels. By combining ontological precision with graph-based representation learning, we can inject actionable semantic structure directly into emotion classifiers. The LLM-driven augmentation pipeline scales cleanly. The GNN fusion strategies are lightweight and interpretable, and the performance gains are statistically robust. If you're building models for market signal detection, behavioral finance research, or automated sentiment-driven trading systems, treating opinion as a structured graph rather than a flat token sequence isn't just an optimization. It's a necessity. The code, dataset augmentations, and full experimental breakdown are available for review. If you're working on opinion-aware financial NLP or graph-enhanced language models, I'd recommend digging into the hyperparameter sweeps and fusion ablations. The marginal gains in nuanced emotion classification compound quickly when you scale this to real-time microblog streams. Thanks for watching, and I'll see you in the next deep dive.